Hello and welcome. In a previous video, we took a look at the definition of the directional derivative, and we simplified it down to just being a pretty quick computational form that involved two vectors. Now, one of those vectors was just the direction we wanted to travel in. We made sure that that was a unit vector. But the other vector we denoted as nabla f, or we called it the gradient of f. Now, in this video, we're going to be focusing on the main properties of that gradient of f and what that vector actually implies, and also even how to visualize it. So why don't we start off with the definition again? If we have a fully differentiable function f, then the gradient of f, which we denote as nabla f, is a vector that consists of all of the first order partial derivatives of that function. So for instance, if we have a function of two variables, f of x comma y, then the gradient of f at any arbitrary x and y would be a vector consisting of f partial x and f partial y. If we wanted to take a look at a function of three variables, f of x comma y comma z, then nabla f, or the gradient of f at an arbitrary x, y, z, would be a vector consisting of f partial x, f partial y, and f partial z. And this can be extended into functions of n variables. In that case, we would number the variables from x1 to xn perhaps, and we might just number all of the partial derivatives, f1, f2, all the way up to fn. Now, the interesting distinction here about these functions on the left is that they take a point in n-dimensional space and they give us back just a single value. We call them scalar functions. Their domain would be some subset of Rn, and their range would be some subset of just R. So when we have x and y as our input, we typically call that output z, but it's just a real number. However, everything in red here is also a function in the fact that it takes input and it gives us a unique output. The input is still just going to be some point in n-dimensional space. However, the output is actually a vector. So these are going to be called vector functions. No big surprise there probably. What we take is a point in n-dimensional space as our input, and we get a vector in n-dimensional space as our output. And there's going to be our domain and range of these functions. And we're going to take a look at how to visualize this gradient as a function, and also what it tells us as a direction at any given point in the domain of Rn. But first, why don't we just focus a little bit on nabla. That triangular symbol just looks like an upside down delta. Now, we've seen something kind of similar to that before in single variable calculus. In single variable calculus, when we want to find the derivative of some quantity or some function, then we may apply the operator d by dx. For instance, if we apply d by dx to the function f, then the result is the derivative, f prime of x. And we've seen that same kind of operator for partial derivatives, del by del x. Now, for multivariate functions, we have something very similar. In this case, we have the vector differential operator, which is nabla. And when we apply that to a function of, let's say, three variables, f of x comma y comma z, then the result of applying that operator is a vector consisting of the partial derivatives. And on its own, that nabla is kind of acting like three partial derivative operators. We can almost imagine that nabla is like a vector that consists of del by del x, del by del y, and del by del z. But let's not actually call it a vector necessarily, because a vector should consist of three real numbers in R3. And these are not numbers, they're operators. So this nabla operator is essentially just a collection of the partial differential operators. And we're going to be seeing nabla again in future videos and potentially in future courses. That is something that we can apply even more than once, and we can apply it to different kinds of functions in unique ways. But for right now, our main application is for the gradient of f. And let's see if we can visualize that gradient. Since the gradient of f is a vector function, its output is called a vector field. And that's going to be true for the output of any vector function. Now, of course, when we try to visualize any of these concepts in 3 or more dimensions, it's very difficult to kind of get that out of a 2-dimensional screen. So why don't we stick to a pretty simple example where we have a function of maybe just 2 variables, and let's see if we can graph or visualize this vector field on an xy plane. For a basic example, let's go with a common shape such as maybe a hyperbolic paraboloid. F of x comma y is equal to x squared minus y squared. That's our pretty classic saddle shape. If you want to look at cross sections, then in the xz plane, we end up with z equal x squared, and that's a parabola opening upward. And if we want to look at a cross section in the yz plane, we get z equals negative y squared, and that's a parabola opening downward. That's what gives us that saddle shape. Now, right away, it's not exactly difficult to at least numerically calculate the gradient of f. That is simply just the vector 2x comma negative 2y. But remember, this is a function. Even when we just write gradient of f, it's still the gradient of f evaluated at a point xy. And we can plug in whatever point xy that we like. The domain of f is all of R2, so we're pretty free to pick any point that we want, plug it in, and calculate the output as a vector. The tricky part becomes, how do we plot that output vector on the xy plane? Well, let's do a couple quick examples. We could potentially just make a table of values here on the right, but it's also pretty easy just to do mentally. If we pick a point 0, 0 as our input and plug that into the gradient of f, then the output is a vector 0, 0. That's just the 0 vector. It has a length of 0 and it doesn't have a definable direction. So we would just leave that as a single dot there. We can't really plot that vector at all. But why don't we pick a point that's a little bit easier to work with, such as maybe the point 1, 0. If we plug that as our input into the gradient function, then we get the vector 2, 0. And that would be a vector of length 2 pointing straight to the right along the x-axis. In triangular brackets, that is 2, 0. Okay, well, maybe let's try picking one more point, maybe at 0, 1. If we want to plug 0, 1 into our gradient of f function, then we get the vector 0, negative 2. That's going to be a vector going straight through the origin, pointing 2 units downward from the point 0, 1. And we're always plotting these vectors with the initial point that is our input into the function. Now, unfortunately, you can see that that vector overlaps one of the other points that we already picked. And that's what makes plotting a vector field pretty difficult by hand. Let's just try one more point here at the point 1, 1. And you'll see that when you plug 1, 1 into our gradient, then we get the vector 2, negative 2. Now that's an even longer vector than the two we've already looked at. That's 2 units to the right and 2 units down, and so it's going to be quite long, and it's going to cross over one of our previous vectors. So what we typically do is we actually just scale these vectors back so it's easy just to determine their direction, but not quite as easy to determine their magnitude by looking at them. Scaling all these vectors back, and then of course we could go ahead and plot even more points on there and hopefully be able to manage all of these little vector arrows so that they don't cross paths with each other. So maybe we would try to plug in all of these other points that is just along a grid pattern here. Negative 1, 1, negative 1, 0, negative 1, negative 1, and so on. After drawing those arrows, you can kind of get a sense of at least the direction of the gradient at each of those points. And the farther we go away from the origin, the larger the values of x and y are that we're going to plug in. That means that those vectors should be even longer length, and we may have to scale everything even further back. So as you can imagine, trying to sketch a vector field, even just in 2 dimensions by hand, is pretty tedious and it's not exactly practical. Instead, let's take a look at Maple and see if we can get some sort of software to go ahead and plot that gradient for us, plot the whole vector field. And maybe we can get a good sense as to some of the important properties of the gradient vector at every single point. It is somehow related to the actual surface z equals f of x comma y, but it's not immediately obvious. Turning over to Maple, we're going to go ahead and use the plots package because we're going to have some pretty interesting looking plots and specialized plotting commands that we want to take advantage of. Let's define the function x squared minus y squared. That's our hyperbolic paraboloid. First of all, let's just take a look at what that saddle looks like. Good old plot 3D command, and we can at least kind of get a sense of the parabolic shape. We've got a parabola opening upwards on the xz plane, and a parabola opening downwards on the yz plane. Now, in this plots package, we also have a command just called Grad Plot. You can probably imagine what that does. It just simply plots this vector field corresponding to the gradient of f. And here is that vector field. This is the gradient of f at a very dense looking grid here. This is just going from -3 to +3, and you can see that we're plotting just dozens of arrows across the x-axis and across the y-axis. And you get a pretty good sense of where they're pointing, but none of these arrows are drawn exactly to scale. However, they are at least proportionally accurate to one another. The smaller magnitude vectors towards the origin and larger magnitude vectors away from the origin. Now, how are these two graphs related? We've got our hyperbolic paraboloid, and we've got gradient vectors that seem to have this interesting asymptotic behavior, and we've already seen that the actual gradient vectors themselves point exactly along the x and y axes for any points along the two axes. Why don't we go ahead and hide this gradient plot for a second and call it P1. And now we're going to take a look at another command in the plots package called contour plot. That is literally just going to give us a contour diagram. You can see that we can actually find the height of the function by looking at each of the corresponding curves. We've got a height from -7 to -5 to -3, and you can see that that's sort of color coded, going from a low value to a high value. And down here at the bottom is the same exact values of z. Z -7, z of -5, and so on, increasing as we go through. Well, that seems to be the same kind of direction that the gradient was pointing in. So why don't we overlap these two graphs together? We'll hide that output and call that output P2 and display both of those graphs on the same set of axes. And sure enough, you can see that these gradient vectors are always pointing in the direction of traveling uphill, going from z -7 to z -5 to z -3 and so on. And if we wanted to even potentially zoom in further, we can get a good sense that if we take a look at scaling this as 1-to-1, that those vectors are exactly perpendicular to the level curves. We could zoom right in there. That looks like a right angle to me. Maybe we'll just zoom back out here again. So the gradient vector is giving us a compass direction of how to get uphill on this surface. You notice that, however, right in the middle there, the gradient was 0. It has a really tough time figuring out which direction is uphill, but that's also where we get an interesting behavior of the function. Tangent plane at that point is 0. Now let's see if we can take all of these observations and make sense of them. Let's take a look back at the notes here and see if we can deduce why each of those gradient vectors may be pointing uphill and why they are orthogonal to those level curves. The explanation comes back to the fact that the directional derivative can be computed using a dot product. And if we remember, the dot product of two vectors is a scalar, and that is just simply computed as the magnitude of one vector times the magnitude of the other vector times cosine of theta, where theta is the angle between the two vectors. Theta would be between 0 and pi. If that's the case, then since the directional derivative is a dot product of the gradient of f and u hat, then we can write the directional derivative in this form of the magnitude of the gradient times the magnitude of u hat times cosine theta. However, remember that u hat was chosen to be a unit vector. So that means that the directional derivative of f in the direction of u hat at some arbitrary point x naught, y naught is just the magnitude of the gradient at that point times cosine theta. Theta is still the angle between the gradient vector and the direction in which we want to travel. Let's take a look at a few examples of different angles. Let's start off with theta equal to 0. If that's the case, then our gradient vector and our unit vector are pointing in exactly the same direction at the point x naught, y naught. And if we were to calculate the directional derivative at that point in time, since cosine of 0 is just equal to 1, then the directional derivative of f in that direction u hat would just be the magnitude of the gradient vector. If we wanted to let maybe theta be 9 degrees or pi over 2, then the direction in which we're taking the directional derivative is going to be perpendicular to our gradient vector. In this case, with an angle of pi over 2, then cosine of theta will just be equal to 0, and the directional derivative of f in this direction is 0. That means that the value of f is not changing in this particular direction vector. Finally, why don't we go ahead and max out that angle so that it goes all the way to pi. In this example, we're choosing a direction that is exactly opposite to the direction of the gradient vector. Now, when we plug theta equals pi into the formula for the directional derivative, then cosine of theta is minus 1, and the directional derivative is simply equal to the magnitude of the gradient vector and negated. So we've gone from cosine of theta equaling to 1, down to 0, down to negative 1. And so this is actually showing us that the maximum rate of change of f occurs when our direction is in the direction of the gradient. We end up with a rate of change of 0 when our direction is perpendicular to the gradient. And we end up with the lowest or minimum rate of change of f when our direction is opposite to the direction of the gradient vector. So this is exactly what we saw when we overlapped our level curves and the vector field for the gradient. You can see that the gradient vector is always pointing in the direction of traveling uphill in the steepest way possible. And we can also see it is orthogonal to level curves. Level curves are a direction in which the function is not changing, and that is perpendicular to the gradient. That's what we saw when we overlap the two graphs. So it's kind of a neat little compass direction. It's telling us how to get uphill in the steepest way possible. And not only that, the magnitude of the gradient tells us the steepest slope as well. Why don't we write down these findings as a few of the major properties of the gradient then? The first major takeaway from seeing this gradient and visualizing it is that at any point P where our function is fully differentiable, the gradient of f points in the direction of the greatest rate of change of f. And that is not just true for a function of two variables. This is generally true for functions of any number of variables. The gradient of f is a vector in Rn that tells us the direction in which f increases at the fastest rate. Second property is that the actual magnitude of the gradient is very important. The directional derivative has a maximum value equal to the norm or magnitude of nabla f, and the directional derivative has a minimum value equal to the negation of that magnitude. Finally, we also have seen that, at least in R2, the gradient of f is orthogonal to the level curves, where f of x comma y equals some constant value. But we can also extend that to R3. It's just that in 3 dimensions, if we have a function of 3 variables equal to a constant, then that is some kind of surface. It's just a surface that's in implicit form. Some function of x, y, z equals k is going to give us points that form a surface, and the gradient of f is going to be orthogonal to that surface at a given point. Now, the really handy thing about that last property, especially in 3 dimensions, is we're often concerned with finding the equation of the tangent plane to a surface. And we did have an equation that would allow us to compute that. But for surfaces that might be in an implicit form already with a combination of x, y's, and z's equal to a constant, it's really easy to find at least a normal vector. That normal vector is just the gradient of f, and with a normal vector and a point, then sure, we can get the equation of the tangent plane very quickly. In fact, in 2 dimensions, for an implicit curve, we can find the equation of the tangent line very quickly. So let's try that out. With a gradient, finding tangent lines and tangent planes should be a much quicker process now. Let's take a look at a couple examples of maybe finding a tangent line to a curve or a tangent plane to a surface at a given point, where either the curve or the surface may be given in implicit form. One of my favorite examples of an implicit curve might be an elliptic curve. It's not overly complicated. It's just going to be something maybe of the form y squared equals a cubic in x. However, we can't just solve for y easily. Square rooting both sides is not going to be a one-to-one operation, so we can't just write this as a function y equals a function of x. So let's just leave this function as it is and see if we can find the equation of the tangent line to this elliptic curve at a given point 0, 3. If we want to use that last property that we came up with for gradients, we're going to want to make sure that this implicit form is at least of the form of f of x, y equals k. So why don't we move just about every term over to the left-hand side, but it's okay to leave the 9. That'll be our k, and now we can treat this as a level curve of a 2-variable function. This is literally just f of x, y equals 9, where f of x, y is y squared minus 8x cubed plus 10x. Now, even though we are trying to find a tangent line, what we can do is find a normal vector. That's actually just going to be perpendicular to the curve. But from there, we should be able to go and use a very similar strategy for how we found the equation of a plane to be able to find the equation of a line. It's just that all of these vectors are going to be in 2 dimensions. From the property of our gradient, the gradient of f at the point 0, 3 is going to be orthogonal to this level curve that passes through that point. And a gradient vector is pretty easy to calculate. We just have the function y squared minus 8x cubed plus 10x. So our gradient of f is just going to be negative 24x squared by the power rule plus 10. And then our y component will just be 2y. That's super quick to calculate. And now we can just plug in the point 0, 3. That gives us the vector 10, 6. Now let's not forget, the way we found a plane in a previous video was just by knowing that we need a normal vector and the position vector of a point on the plane. But this can also be brought back 1 dimension to even just give us the equation of a line in 2 dimensions. Our normal vector, though, is going to be our gradient, 10, 6. So that'll get substituted in there for n. And our r0 is the position of the point that we have, in this case, on a curve, 0, 3. So we're going to be taking the dot product of our gradient vector, 10, 6, and the vector x minus 0, y minus 3, and we'll set that equal to 0. When we calculate the dot product, then we multiply component-wise. 10 times x plus 6 times y minus 3. That gives us 10x plus 6y minus 18 equals 0, and that is the equation of our tangent line. Of course, we could simplify that by dividing everything by 2 if we want. And if we're happier to write that in y equals mx plus b form, then sure, we can go ahead and solve for y. And we find out that we have a slope of negative 5/3 and a y-intercept of 18. And you'll notice 5/3 is equivalent to 10/6. The actual slope of the tangent line is negative 10/6 when the gradient was 10, 6. It's kind of our nice relationship there. The gradient vector goes over 10 and up 6, so it has a slope of 6/10 or 3/5. And our perpendicular slope, which is the slope of the tangent line, is negative 5/3. Now, it might not have been terrible to actually just get the equation of the tangent line using methods that we learned in first year calculus with just single variable functions. That implicit differentiation can even also be skipped from what we've seen previously from the multivariable chain rule. You have all of these new options that allow you to rethink how you may have done derivatives and tangent lines from single variable calculus though. But what's really going to be handy now is in multivariable calculus, the ability to get the equation of a tangent plane to some implicit function that defines a surface in R3. Let's take a look at a very straightforward example of an implicit surface. X squared plus 4y squared plus z squared equals 9. Well, if we didn't have that 4 there, that would be a sphere. But because we've slightly stretched or shrunk this in one direction, this is now called an ellipsoid. And on that ellipsoid, we have the point 2, 1, -1. You can double check that that does satisfy the equation. What if we want to find the equation of the tangent plane then? Well, this is already in the form of a function of 3 variables equals a constant. So let's let f of x, y, z equal the function x squared plus 4y squared plus z squared, so that the point that we have is really just a point on a level surface of the function where that function equals 9. We'll use the exact same strategy as before. We'll take a look at the gradient of f. That's 2x, 8y, and 2z. We'll plug the point in, and this vector 4, 8, -2 is orthogonal or perpendicular to that surface. It's perpendicular to the ellipsoid at that point. So we've got the two pieces of information that we need to get a plane already. We have a normal vector and we have a point. We'll plug 4, 8, -2 into the normal vector, and we'll form the vector r minus r naught and set the dot product equal to 0. R minus r naught will be x minus 2, y minus 1, and z plus 1, which is really just z minus -1. Multiplying component-wise, we can expand that out, and then we can also collect terms, and we'll have the equation of a plane. 4x plus 8y minus 2z equals 18. Once again, we could go ahead and divide everything by 2, and of course it's up to you. If you want this to look like a function z equals f of x, y, then you can do that as well. Now, this should get you the exact same result as if you had gone and done implicit differentiation or multivariable chain rule to find the partial derivatives del z by del x and del z by del y and plug them into the formula for the equation of the tangent plane, or the linearization of the ellipsoid at that point. But you can probably see that this is just so much faster. All you need to do is treat it as a function of 3 variables equal to a constant as a level curve, and use the gradient as our normal vector. One last thing that you can also do that's kind of related to this idea of the tangent plane. You can actually use gradients to show that two surfaces are tangent to each other at a point. Where if two surfaces are tangent to each other at a point, they would share the same tangent plane. Let's suppose that we have two surfaces in implicit form. Maybe f of x, y, z equals a constant a, and our other surface, g of x, y, z equals some constant b. Now, if they are tangent to each other, then they both have the same tangent plane. If that's the case, then the gradient of f and gradient of g are both orthogonal to that plane and must be parallel to each other. Now, by definition of parallel, that just means that the gradient of f is some scalar multiple of the gradient of g. Now, hold on to that fact because we're going to be seeing it again in a future video when we take a look at optimization. In fact, this is still true even just for curves. If two curves share the same tangent line, in which case they are tangent to each other, then their gradient vectors are going to be parallel to one another. So we'll see that again in the future. But for hopefully right now, you get a pretty good sense of what the gradient vector is for. And the idea of that vector differential operator as being just as important as d by dx in single variable calculus. That gradient vector points you in the direction of maximum increase. which is also useful for optimization. If we're taking a look to try to find the maximum of something, that gradient vector is going to be very useful for that. But stay tuned, we have lots more to take a look at with that gradient. So thanks for watching, and I'll see you in the next video.